All right, good morning. Any questions so far? All right, so let's run through ODP 213. So this is posted on Canvas now. This opened up at 10 o'clock. Oh, my mic is off. Yes, indeed. All right, there we go. I'm back. Good morning. All right, any questions? Hopefully you can hear me. Cool. Can or can't hear me? I can hear you now. Okay, cool. All right, let's talk about ODP 213. So this is posted on Canvas and is due tomorrow morning at 10. And there were some issues with it a few minutes ago, but those issues are fixed. So this should be up and running and available to assess. So 213, we're playing with hash functions, right? No surprise here. So this and the next ODP, you're going to create a hash function that takes in a string and returns an integer. So the prototype is straightforward, right? Your function is called hash, takes a char star, which is a string, returns an int. And your hash function is the one that we were discussing previously. So take the sum from I equals 0 to your string length minus 1 of just each character in your string. Add those up and then reduce modulo 31. A semi-random number, but it's prime. So if your string is HELLO, then what's the string length of that? What would string length give us back if we said string length, quote, HELLO? Five, perfect, right? It does not count the null terminator, and this string HELLO has just 5 characters. There's no new line at the end unless I put a \n, for example. Or if I used fgets and I typed HELLO, fgets would add a new line at the end, and then string length would be 6. But this is just 5 characters, and so the index of each character, starting from 0, the last character is at index 4. So string length is 5, the last character is at index 4. So there's a pattern, right? String length minus 1 is going to tell you the index of the last character. So that's why I'm keep putting the string length str minus 1 in this summation symbol. So if you did a for loop, you could go from I equals 0, I less than or equal to this value. Usually when we do a for loop, we just say less than string length, because that means stop after you've done this value. So either way. So add up the characters, reduce mod 31, that's the value of your hash function. Okay, so that's pretty straightforward, but there's some possible gotchas in here. So one gotcha is, okay, to add the ASCII characters of your string, just, you know, sum equals sum plus string bracket I. Don't cast to integers, don't convert, don't do scanfs or anything weird like that. Just add each of these things, str bracket I, to a running sum, which is an integer, and it will take the ASCII code and add that as an integer. Don't make your running sum an integer, make your a character. Make your running sum an integer, don't make it a character, right? And if you just add str bracket I, yeah, that's a character, but the compiler will figure out how to add that value as an int. So don't do too much work here, right? Just treat it as an array and just add each of the elements. All right, I've put some examples in here. One, to help you understand the concept. Two, to give you test cases. So if my string consisted of just one character, which was the letter A, so double quote A, right, that should hash to a value of 3. Why? Because the ASCII value of A is 65, and 65 mod 31 is 3. Right? In other words, it's 2 times 31 gets you up to 62. There's 3 left over. Here's some 215 flashback. So a string just containing A should hash to a 3. A string containing A, B, C, 3 characters total, should hash to a 12. Because the ASCII values are 65, 6, and 7, those add up to 198. That's 12 more than a multiple of 31. If you were to hash CAB or CBA or BAC, you should also get a 12, because the order in which you add these doesn't affect your hash function. Right, we're just doing this straight summation, so the order in which I add them doesn't affect the sum, so the hash function value won't change. If you do uppercase HELLO 5 letters, you add up those ASCII values, it turns out to be a multiple of 31, so the hash value should be 0. So here's some other strings you can play with, right, to test your hash function. And an easy way to test this would be something like this. Just plain old print statements. So I'm going to call my hash function with 5 characters, the string HELLO. That's going to give me an integer, and I'm going to print out hash value for hello equals, and that %d will get replaced with the value of my hash function. And this should print hash value for hello equals 0. And then if I do the same thing but I use hello like this, it should say hash value for hello equals 4. Okay, that's a really kind of, you know, solid way to test your hash function using these particular values. Let me tell you one other gotcha here, right? Don't do anything as far as special treatment of any characters. Don't treat new line as something special. Don't look for nulls. Don't, you know, do string length -2 to get rid of a new line. Nothing. Just add the ASCII characters, reduce mod 31, return that. Okay? The simplest possible way you can think of to do this is probably the one that's going to work and is going to be correct. What makes this tricky sometimes is if you want a more general test function, you could write a main program that says, you know, enter a string, does an fgets, passes that string to hash, prints out the value. If you do that and you try to hash hello, you're not going to get 0, you're going to get 10. If you do help, you're not going to get 1, you're going to get 11. Because fgets adds a new line. And if I do that, if I say fgets string and then hash string, and I type hello, enter, my hash function is not being given the string HELLO, it's being given the string HELLO\n. There's nothing wrong with your hash function. It's a problem, if you see that as a problem, in how you're interpreting the results. So if you want to be able to see if these things give you the values that you want, then in your test program, you should chop off that new line after you come back from fgets. But don't change your hash function to try to get these values to come out. Write your hash function in a way that looks like it should work. If it doesn't work, if you're off by 10, the solution is not to subtract 10 from your hash function. The solution is not to chop off the last character in the string that you're hashing, right? So don't ever change code that you think should work just to patch up some symptom. So fgets would only be needed if we make our own test bed exactly. There's no fgets in the hash function itself. So I'm only talking about if you're writing a test function and you want to do something more general than this, just remember fgets adds a new line. And so when you hash the result of fgets, you're not going to see these. You're going to see an extra 10. All right, so that's the ODP. ODP 213, there's the test bed. The README is under temp, ODP 213 README. I updated Canvas to have the right name for that. Go ahead and assess, and you should be good to go. Tomorrow's ODP will be almost the same thing, but our hash function will be slightly more difficult. It will take in a probe value, which will modify the hash function slightly. All right, any questions on that or anything else we've done so far? Good to go. All right, so let's start developing some algorithms for working with our hash tables. So the way we're thinking of this, we've got a hash table that's really just an array. And we need different things to be stored in this array, so let's make a structure. I'm just going to call it H entry for hash entry. And we know that we're going to store things in pairs. And these are usually called key and value. Well, at least usually today. So there's a key value pair. Let's just suppose they're strings. They can be pretty much anything. Let's see, quick question on ODP. Did you say we cannot get the ASCII code by casting to int? You can cast to int, but the compiler will do that for you. It's generally legal to add a character to an int, but not necessarily the other way around. But don't try to convert it to an int using, like, you know, sprintf or anything like that, or scanf. Welcome. All right, so I'm going to make a structure called hash entry that contains keys and values, right? And so htable would be an array of H entries. However big we need it. Now we could declare this as a static array like this, or we could make it a pointer to a struct H entry, and then we could call malloc to give it some size at runtime. Either way, I'm not going to worry about it today. We're going to stay kind of high level and look at algorithms rather than a lot of C code, but we're going to get into some of the C code anyway. All right, so here's what our hash table looks like. And there's some other stuff in here. We've already seen the notion of a valid flag or an in-use flag. So before we develop this set of code, let's look at the interface. So what's this look like as an abstract data type in our main program? So abstract data type, we're thinking from the user perspective, from the perspective of a main program that wants to use a hash. What kinds of things do we want to do? And so there's some sort of initialization. And sometimes, our init would tell us how big do we want the hash table to be. So you could put it in a starting size, for example, but some kind of initialization to create, this table and deal with the valid flags and things like that. To store information, we usually think of this as put. And put takes a pair of things. A key and a value. And that returns, probably some success flag. An int maybe. Which says were we able to save that key value pair. So we're always thinking of pairs, right? We're not just going to store, some piece of information. We're going to store some piece of information associated with some key. So we can store information. We can also get information. And typically we go in with the key and we retrieve the value. Sometimes you want to go in with a value and retrieve a key, and a lot of hash implementations give you support for that. We may want to search for a key, or we might write the get value so that it can tell us whether or not it succeeded in getting a value for that key, and we could use that as a search. But for now, I'll think of search as different. What else do we want to do with a hash? Give me some more functions. Delete, perfect. We want to remove data. And again, we could return a success value, or we could assume you're going to call search before you call remove. Either way. All right, modify data. So we could have another version of put called modify, which lets us modify the value associated with a key. Or we could say if you put a value with a key that's already there, it will be a modify operation. So some way to modify. Or you could remove the key and put a new one. Add we already have, that's what the put function does. But I changed it to put get because those are sort of the usual names you see with hashes. That's okay. So the one other thing that's missing after remove is some way to view the data that's in here. And remember in 224 when we played with associative arrays, you were building a index of phrases and a tally of how many times each phrase occurred. And when you found a phrase, you used that as an index into an associative array, a hash, and you bumped up the counter. So that kept track of how many times each phrase occurred. When you were done with the program, then we wanted to print out the whole index of phrases along with how many times each phrase occurred. To do that, we needed some way to go through our array and find all of the phrases that were stored in there. In other words, we want to go through and we want to find all of the keys. And we've got to provide the user a way to do that. Because the user can't come into this H table and say, you know, for I equals 0 to 30, if H table I dot valid is 1, then print out the key and value pair. That's not allowed. The user never sees this. This is completely hidden from view. Abstract data type. So this is nothing to do with the ADT. The user's whole interface with the hash has to be through a set of functions that we define and provide. So a simple way to do this would be just like a print function. But that's not very useful. Because, you know, that comes out in one format, in one order, it prints everything, it prints it to a certain place. Probably not what the user wants. What we really want, more generally, is some kind of traverse. Or an iterator. And we'll have to talk about iterators later. We'll definitely talk about them in 223. But most data structures come with some sort of mechanism to say, hey, give me the stuff that's in this structure one thing at a time. So here would be a really useful iterator on a hash table. Hey, give me a key, any key. Just give me some key that's in there. Okay, give me another key. Give me another key, give me another key. Oh, you're done? There's no more keys left? Okay, thanks. All right, that's an iterator. And we did that in 224 with our associative arrays. There was this funny, you know, syntax with @ signs and $ and percents and brackets that basically said, give me the next key, right? So we did a for loop that iterated over all of the keys in here. So we want some kind of iterator, but for now we're just going to think about print. Okay, we won't get fancier than that. So this is what a main program would see to interact with a hash, and there could be other things as well. We might want to know if the hash is full, and we might want a way to expand the hash to grow it, to say, hey, you know, make this table bigger. Or that might happen automatically for us. All right, so the init function is pretty straightforward. If we have a statically allocated array like this, we don't need to call malloc. But if we defined struct h entry to just be h table to be a pointer to a struct h entry, then init would want to call malloc and allocate size for however many entries we want. And it might be something that the user specifies, or it might be hardwired. The initial size of the hash is 31, something like that. So maybe allocate space. Maybe we don't have to. But the main thing we have to do is set those valid flags. So we need to go through and we need to mark each of these as a 0. So that even though there is something stored in here and there's something stored in here, and it's possible that the thing stored in here might actually be a key that's meaningful to us, we're going to look at the valid flag and say, nope, that's not actually part of the table. So we empty this table out by clearing the valid bits. And that's really the main thing that init has to do. All right, so let's look at put. Alright, we've got a key and a value pair. We want to store the value somewhere in our hash table along with the key. How do we figure out where in the hash table we should store this information? So how do we figure out where to store it? I'm full of questions today, apparently. My earlier section, I was just asking questions the whole time. I'm shifting into that mode. Should we store it at location 0? Should we not store it and play a trick on the user? We could have separate arrays for key, valid, and value, or we could make a structure that contains all three of those fields, and then just have an array of that structure. And let's say I've set hash size to be 31. So for this particular example, there can be 31 spots available in this array. And maybe I would, keep my code clean and use h size in here instead of 31. So yeah, there's 31 possible places to store. So how do we know which one of those 31 locations we should use? So hash the key and put it at the index that corresponds to the output value of the hash. Perfect. So we have this hash function. The reason the hash function exists is so that we can take a key and it will tell us where we should store that key in the table. That's what the hash function does. It maps from the space of all possible keys to the space of all possible indices. So let's do index equals hash key. And so we want to store our information at that location. Okay, so what does this look like? Basically, something like this. So h table bracket index dot key equals key. But we can't really do it like this. This is pseudocode. If we want to do this in C, we got to do something more. So why wouldn't this work as C code? There's a couple of problems here. One of them's a little subtle, the other one's extremely subtle. Because it's a string, right? And we can't use equals to copy the contents of one string to another. So this would change this to point to whatever that is pointing to, which means that if we call our function again with a different value of key, suddenly the thing we stored in here will change and it gets all goofy. So what do we really need to do? we need to use string copy, which says character by character, take each character from this string and copy it to a character of that string. The other problem with this is I've defined my hash entry to have fields called key and value, which are simply character pointers. But unless I point those to something, I'm going to get a seg fault when I try to string copy into key or value. So I need to do some kind of malloc. Now I could just say, you know, key is a character of 50 characters and value is a character of 50 characters, an array. But there's two problems with that. One, you know, I'm limiting the size of my key and value to be 50 characters. And two, if my key is only 2 characters, I'm wasting 48 bytes of memory. So generally we would make these pointers to characters, and then when we're ready to store something in there with string copy, we would call malloc first to allocate space. Does that make sense so far? Alright, so how much space do I want to allocate? This is the more subtle part. I'm going to store a key at this key piece of the structure, the H entry, at the index in H table. I need to allocate space for it because right now that's just a car star. So how much space do I want to allocate? Take a shot if you're not sure. Let's work our way towards an answer. It would be an int. Well, what would be an int? So the argument to malloc is an int. Size of hash value. Okay, that's close. Size of should only be used with a type of variable. So let's not use it on a variable name, let's only use it on a type. And I have 2 car pointers, key and value. And we're just looking at key right now, and I want to store it in my hash table at some spot here. Well, each of these things is a car pointer. So size of struct H table would be big, because that's going to be 31 hash entries. So it could be smaller than that. So let's suppose key equals let's suppose my key is hello. And I'm going to copy this string into htable at some index dot key, which is a car star. So what we're doing here is saying htable some index dot key equals, we're going to try to have this point to some location in memory. How big does that location have to be if my string is hello, if my key is hello? Size of car times string length of key, I like that. That's sounding pretty good. So allocate however much stuff we need to store one character times the number of characters in our string. So if our key was hello, size of car is 1, takes 1 byte. String length of hello is 5. This would allocate 5 bytes. But you do have to add 1. And that's the really subtle part that will definitely bite hard at 3 a.m. Got to add 1 more because we have to store the null terminator also. If we only store HELLO, then when we come back and we look at the key, we have no way of knowing if it was HELLO or HELLO with some other stuff. So we have to actually store 1 more character. So we have to malloc string length plus 1. So there's details here. We're not going to worry about them today, but I'm going to mention them so that when we mention them again, when we are worrying about details, you'll have seen them at least once. All right, so the goal here, right, find the index to store the key, and then store the key and value at that index, and then set the valid flag. All right, so I hash my index. Let's say it gives me 2. So I store the key, hello. I store the value, you know, whatever. I don't know why we're hashing the word hello, so we'll just store it with the word blah. And we set the valid flag to be 1. All right, so that's a good start on the put function. There's one detail that we're missing in here, though. And it relates to the valid flag. So we need to do one other thing in here before we actually can store the key value pair. We need to check to see if something's already there. Perfect. Excellent. So we take our key, we hash it to an index location, but we got to check and see if there's already something in that location. We've got to check for a collision. All right, so checking for the collision is easy. Just check to see if that location in the hash table, if its valid flag is equal to 1. But if it is, what do we do? Well, using the probing, which we talked about yesterday, the idea is we basically rehash. Run through a different hash function and see if we can store it at that location. So let's make our hash function a little more complicated. Let's have it take a second argument, which we call the probe. This will be ODP214, which is the attempt number. So our first hash, we hash with a probe of 0. Check for a collision. And I'm going to rewrite this once we're done scribbling. So if the valid bit is set on that location, then rehash and try again. Well, if when we hashed with a probe of 1, we also get a collision, then we need to hash with a probe of 2. And if that gives us a collision, we have to hash with a probe of 3, and we have to keep going. So this should probably be a variable, right? So that we can increment it. And then once we find a value where the valid bit is 0, we can go ahead and store the key, store the value, set the valid bit, and we're done. So let's write that up a little cleaner. So let's put key value. So I'll make a probe variable. That's our attempt number. We'll hash. And then we want to keep doing this loop until this valid bit is clear. So let's just think of this as a while. So while at that index, the valid bit is asserted. So I'm treating this like a Boolean, even though it's an int. So while this is asserted, what do we want to do? Increment the probe. And calculate your new index. Go back and try it again. And now when we come out of that, we've got the index that we want to use to store. We know the valid bit is set to 0, so go ahead and just do your copies. And I'm going to do a symbol like this to say, you know, do what you have to do to copy your key into the key piece of that H entry. And do the same thing for data. And set the valid equal to 1. And I'm going to return a 1 to say success. So there's only one thing missing from this now. So what are we missing? There's a problem with this code. There's a problem somewhere in here. So what can go wrong in here? What's the most common thing that goes wrong with while loops? Infinite loops, yeah. We won't go out of bounds as long as our hash function always gives us a number, in this case between 0 and 30. We won't go out of bounds. But when you've got a while loop, there's always a possibility of an infinite loop. And in this case, there's no exit condition from here until we find a spot where the valid bit is 0. Well, what happens if all of these valid bits are 1? In other words, if our table is full, this is just going to keep spinning and spinning and spinning, looking for more and more, you know, looking at different locations to try to find an open spot, and it's never going to find one. So that's going to loop forever. So the other giveaway for that is this function returns an integer. We have a return 1 at the end. There's never any place where we return a 0. And that kind of tells you, hey, you know, I must have forgotten to check for failure. What's the failure? Trying to put into a table where there's no space. So that would also point you back to your while loop. So we could do something in here like if our probe is bigger than maximum number of tries that you want, then let's just return 0 to say success. And there's different ways you can do this. You could keep track of how full your table is, and in the beginning of put you could just look to see if there's no space left. And if there isn't, you could just say we're out of space, return a 0. Don't say out of space, just return a 0. Don't print things from these functions. A good hash function will try every single key location before repeating. It won't try them in order. It will probably try them, you know, bouncing around, but a well-written function would try these in you know, some order, but it would try every single spot. If there's anywhere in here where the valid is 0, a well-written hash function will find it eventually with some probe value. This is one reason why we want our tables to have a prime length, because it makes it easier to come up with a hash function that won't just repeat. For example, if the hash function always gave us even indices, we might have half our table empty and you know, be stuck in an infinite loop. So we could get out based on a number of max tries, or if we know our hash function is good, we could just see if there's any space in the table, and if there is, believe that this will eventually find it. Alright, so those are more details, things that will come up when we start actually coding this end of the week or next week. So alright, so we want to talk about search tomorrow. We're out of time for today, but we'll talk about search, and search will lead us to delete, and then we'll have a whole compendium of algorithms for working with a hash, and then we can start looking at actual implementation details. Alright, that's all I got. Have a good one. I will see you tomorrow.